This graphical procedure is same as we studied in the MEN, mass exchanger network. There is a rich stream, there is a lean stream. Here it is, there is a hot stream, again there is a cold stream. Okay, similarly here you have to plot T temperature versus H enthalpy curve. So you must draw here temperature and enthalpy curve. So composite curves are temperature enthalpy profiles of heat available in the process through the hot composite curve and heat demands in the process through the cold composite curve with the help of graphical representation. Here it is a graphical representation indicates there are two composite curve. First is the hot composite curve, second is the cold composite curve. So how much heat demands, how much heat required for the particular system, or how much integrated part, or how much you can save the energy you will get by use of this TH curve. Okay, to figure out the heat availability and demand in the process, one has to capture the essence of heat load, hot as well as cold stream, integration and heat flow. In other words, one should search for framework under which integration of heat energy can be performed. So this graphical technique is also based on your first and second law of thermodynamics. I already told you the first and second law of thermodynamics in the previous web session. So you must know that the what is the first law and what is the second law of thermodynamics. So for integration of energy, two parameters are most important: energy, that is enthalpy change, and direction energy flow covered by second law of thermodynamics, high to low temperature, and conserved through maintaining the temperature. So here is the graphical representation of temperature versus delta H. So temperature you have, cause you have data extraction values, that is supply temperature and target values. Okay, and you also have delta H values, MCP delta T. Okay, then how we plot first? If you don't know CP value, specific heat, you can easily calculate by use of this function equation. CP is equals to C0 or A plus B into T plus C into T square plus D into T cube for the particular temperature. So A, B, C, D are the constants, are the heat capacity constants. You will get it from Perry's handbook. So once you have the CP value, you can easily calculate the enthalpy. Okay, now come to the graphical section, graphical representation of only hot stream. Okay, suppose you have one supply temperature is there, that is the 220 degrees Celsius, and target temperature is 60 degrees Celsius. So you must draw one line 220 degrees Celsius to 60 degrees Celsius. So but how we plot? Because I don't know the delta H value, so you must calculate that delta H value by use of MCP delta T. So MCP is nothing but kilojoule per kg degree Kelvin. Okay, so MCP value is given. Suppose it is given 3. So 3 multiplied by 220 minus 60, you will get delta H. So that delta S you must maintain or arrange in the x-axis, and your value, that is nothing but the 220 and 60, you must arrange in the y-axis. Okay, so that is the slope of the proposed line, that is a hot stream, is 1 upon Cp. Similarly, you must draw for cold stream. Similarly, you must draw for cold stream. We'll come to the later. So first of all, I can tell you this line, that is the hot stream, you can move in the graph at the any other section. Doesn't matter. You can move that line any place, but you must keep in mind that your delta H and delta T value should be constant throughout the graph. Doesn't matter if somebody plot in the directly zero scale, or someone plot from 20 degrees Celsius. So there is a difference between the both graphs. So you must keep in mind that delta H value should be constant and delta T value should be constant, or you can move at the anywhere places, or you can shift that curve anywhere in the graph. Then suppose there is again one hot streams are there. There is one again another hot stream, that is 230 to 70 degrees Celsius. So you must have to plot in the same graph by use of the delta H value and delta T value. You will get such kind of graph is there. I can tell you the example in the next session, but you have to have a look out in the general graphical representation how it look like. Okay, now you have to merge these two lines, so you can move the bottom curve, that is bottom hot stream 1, to the left side and join it. Here it is. So there is a total delta H1 plus delta H2, you will get total delta H. Okay, so this is the complete line of H1 and H2. There are two hot streams are there, so these they are merged. So you have to move this hot stream 1 parallelly towards the left to reach the delta H2, that is hot stream 2. Okay, doesn't matter, you can move H2 as well. Hot stream curve you can move right side. Yes, it's possible, you can do it, because delta H value should be constant throughout the graph, and delta T value is also constant throughout the graph. Okay, doesn't matter, somebody shifted the curve from left to right, or somebody shifted the curve right to left, that is also possible.